All right, it's the last lecture for the class. You can see that we have a demo, but we'll do that after covering the last material we need to cover. When we get to the demo part, it's a lot more fun if some of you will pull out a camera and take video, because then I can put it in the video that I put online. So you can take just short clips or whatever with your phone, and then just get it to me somehow, and I'll put it into the YouTube video. All right. So first of all, let's continue what we started talking about taking an inverse Laplace transform or an inverse Fourier transform for rational transfer function. Okay, so we had this idea of doing partial fraction expansion as a way of taking an inverse, and I'm going to go through that here so we understand how to do that. So let's start with continuous time. So we have a Laplace transform. Let's take, for example, h of s equals this function here. So we might have obtained this from like a block diagram, from a differential equation or something. It's a rational Laplace transform. Now let's go through the steps of taking the inverse. First of all, what you want to do is you want to reduce the degree of the numerator so it's less than the denominator. Notice here the numerator and the denominator are both degree 2. Before we get started with partial fraction expansion, you want to simplify using long division to get that degree of the numerator lower. Okay, so if we do one long division step, in other words, we divide out the denominator. We take 3 of the, so I won't write out the long division, but the first step would be to notice that a factor of 3 comes out, and the remainder is going to be, we're going to take 3 times this denominator and subtract it from that numerator, right? And that's going to be exactly this, negative s minus 3, still over the denominator. So this was just one long division step, and now we have the numerator a lower degree than the denominator. So now we can do this partial fraction expansion. The idea is the following, that this is going to equal, the fraction will just split into a constant over, well, I guess, sorry, let me do one step first. We want to now factor the denominator into its poles. Okay, so that equals the following. Now we notice that that becomes an s plus 2 and an s plus 1. In the denominator. Okay, 2 poles. Of course, normally we might be interested in looking where the poles are to see if it's stable. If this is a causal system, would it be stable? What are the values of the poles here? S equals negative 1, s equals negative 2. The real parts are both negative, so yes, it's stable. Okay, if this is a causal system, it's stable. If the real parts are negative. So I'll put a note there. Of course, it's stable because we're assuming causal here. There are more than one region of convergence. How many regions of convergence are there for this Laplace transform? There are 3, because there are 2 poles and they don't occur on the same line, vertical line. So that'll be boundaries for 3 regions of convergence. And the causal one is the one that we noticed is stable. Okay, so what do we do next? We say, well, this equals 3 plus a constant over s plus 2 plus another constant over s plus 1. And we want to find what those constants are. Okay, now to find those constants, we just need, it's just algebra. We could do it this way. We could write out some equations here and say, well, if we multiply these out, we get an a times s plus 1 plus b s plus 2 over s plus 1, s plus 2. And then we can say that's, so this numerator here has to equal minus s minus 3. So we multiply it out, we would get like an a plus b times s plus a plus 2b equals negative s minus 3. And we would lump like terms. We'd say the s terms have to be equal. The other terms have to be equal. So this would be a plus b equals negative 1. And a plus 2b equals negative 3. Okay, so I just want to show you that it is possible to just use elementary algebra and figure out these constants. I'm going to show you a way that often works a little bit quicker than doing that to solve for a and b here. So what we can do actually is a trick that's called the cover-up method. And the way it works is this. If it's quicker, if you don't remember it, just do it the way I showed you in the green there. But assuming you have distinct poles, meaning none of these terms in the denominator is like an s plus 2 squared or anything like that. Okay, so let's say you have distinct poles. Then what you can do is this. We want to say, again, let me just write out explicitly what we're trying to calculate. We're trying to get an a and a b from this fraction. A over s plus 2 plus b over s plus 1. Now what you do is you say, I want to find a. A goes with s plus 2. Okay, so I'm going to cover up s plus 2 in the denominator here. And I'm going to plug in the value of s that would make that term 0. So I'm going to plug in s equals negative 2. All right, so cover this up, meaning ignore it. Should have a big fat hand over that part. And plug in s equals negative 2. The numerator then becomes 2 minus 3. It's negative 1. And the denominator becomes negative 1. So it's negative 1 over negative 1. It's just 1. So we get a equals 1. Let's try the same thing for b. Cover up this term, the s plus 1 term. Ignore it here. And plug in s equals negative 1 in place of s. So we get a 1 minus 3 in the numerator. That's negative 2. And we get a 1 in the denominator. So it's negative 2. And we can check that that's actually the solution to this system here. Right? B is negative 2. Yep, so that works here. So this is, in fact, the answer. Now, maybe you're thinking, why is this weird technique working? And it's actually very straightforward. The reason this works is because if you want to isolate a here, what you can do is multiply both sides of the equation by the denominator s plus 2. What's that going to do? It's going to cancel the s plus 2. That's why we cover it up. It's going to cancel it here. And since no other terms have that in the denominator, it's going to be multiplied by all the rest here. So if we plug in the value of s that makes it 0, everything disappears except a. And that's why the cover-up method works. Okay. In general, if you had, you can have two poles in the same location. That means you can have one of these terms raised to a higher power. And that's fine. Let me just mention so what about higher order poles? Well, actually, let's finish off this inverse. Okay, so now we have values of a. So we can do this. We can say h of s equals 3 plus, what do we have? 1 over s plus 2 minus 2 over s plus 1. And to complete the inverse, we just look in the table. I gave you a table last time, had very few important pairs to remember, and in particular, it had, well, a constant just goes to a delta function, so it's 3 delta of t, and these terms just become e to the negative 2t u of t. And this next one, again, is e to the, we get the multiple of negative 2 out front by linearity, and then it's just e to the negative t u of t. So you just look at the table, and you get that. All right, so there's the impulse response. Okay. Let me mention a few things that will be of, if you were doing this in general, you might have high order poles. And the higher order poles would be something like, let's say, 1 over s, let me just give an example, s plus 2 squared, s plus 1. And now here, to split this out into partial fractions, you'll actually need a constant over s plus 2 and a constant over s plus 2 squared. So you take every lower order pole than the one you started with, and you do that. Okay, so now you just solve for those constants. So that's how you take care of higher order poles. And in our table, we have the inverse of a higher order pole. Okay. If you want to use the cover-up method here, you can only use the cover-up method to determine B and C. You can't determine A from the cover-up method. In other words, you can only do the highest order pole from each of these terms with the cover-up method, and then you just have to use algebra to find the last one. Okay. And I should also mention, we said that there are, starting with this Laplace transform, there are 3 possible regions of convergence. Now, we're usually only going to be caring about the causal one. But if you happen to want to know, how do I find the impulse response of one of those other Laplace transforms? So, for example, let's give a little picture of our poles here. Our poles were at -1, -2. We have 2 zeros. If you look back at this equation, we have 2 zeros, but I'm not going to factor it right now. I haven't done it ahead, so we'd have to factor that to find where the zeros are. The zeros won't affect the region of convergence, so we know the region of convergence is going to be bounded by these poles. And the one we care about, if it's causal, was the one on this side over here, right? And that was stable because it contains the imaginary axis. Well, what if you actually, for some reason, didn't care about the causal system? You knew this was the region of convergence you were trying to take the inverse of. Well, then what you would do is, when you get done with the partial fraction expansion, you get it down to here. This would stay the same, but this term, notice this is the pole right here to the left of the green. You would use the right-sided inverse, just as we've done for that pole. So again, that wouldn't change. But for this pole now is on the right of our region of convergence. You actually would use the left-sided inverse. Okay, the table has both a right-sided inverse and a left-sided one. Okay, so that's what you would do if you weren't only looking at causal systems. Great. Let's do a discrete time example. Oops. Okay, so now of course it's going to be same method. So this is for the Z transform. It's going to be the same method, but let me point out one difference that we'll notice. When we're done with the partial fraction expansion, we're going to get terms like 1 over z minus a, some constant over z minus a. So how do we take the inverse of this? How do we take the inverse Z transform? Well, if you look at the table has things of this form. We know that we have things like this. 1 over 1 minus AZ inverse goes to a to the n u of n. Okay. So then that means that we can take our term 1 over z minus a, and we could make that a z inverse over 1 minus a z inverse. And then we could say, well, this is just something we know from the table, times z inverse. But what does multiplying by z inverse do? In the Z transform, what does it mean to multiply by Z inverse? We have a rule for this. Well, so you're trying to plug in the e to the s to say, you could look at it that way. It's the time delay rule. Z inverse is a delay by 1. Okay, multiplying by Z inverse, of course, multiplying in the Z transform domain is convolution in time. So it's some system that has an impulse response Z inverse, which is just a delay by 1. So this is a delay by 1. So in other words, this would become an minus 1, un minus 1. Okay, so that's how we would deal with that. It's more common to do the following steps that you'll see in my example here. The more common way, which often gives you simpler expressions when you're finished, although they would both be correct. But what you do is do partial fraction expansion. With respect to Z inverse instead of with respect to Z. All right, so you'll see what I mean in the following. Again, both would be correct, but this is just more common because it ends up usually being simpler. So here's the example. Let's say you have h of z is the following. It's been factored for us. This, in fact, this formula came straight from the lecture notes in the last lecture. Okay, we started with a block diagram. We ended up with this. All right. So let's do the inverse, the causal inverse of this. So what we could do is just, we would first notice that the numerator has the same degree as the denominator. So the first thing we'd have to do before partial fraction expansion, if we're doing it with respect to z, first thing we'd have to do is a long division step. Okay, because we'd pull out a constant plus a fraction, and that fraction now would have a numerator that is first order rather than second order. Okay, so you always have to do that first. Make the numerator smaller degree than the denominator. And then we could do our partial fraction expansion from there. But let's change everything into z inverses. So that's going to be this, 1 plus 2z inverse. And this is going to be, we'll keep the 4 out there, 1 minus 3z inverse, 1 plus a quarter z inverse. Okay. Now, what we're going to do is write this, do a partial fraction expansion of this as an a over 1 minus 3z inverse plus a b over 1 plus a quarter z inverse. And to do this, just think of z inverse as the variable. Forget that there's even an inverse there. Just think of z inverse as your variable. Of course, now if z inverse is the variable, the numerator is a lower order than the denominator, so we don't even need to start with long division here. Okay, we can go straight to this. We can do the cover-up method here. So what's a going to be? Well, we cover up this term. We find, what does z inverse have to be here? Well, z inverse will have to be a third. Z would be 3. Okay, z inverse is a third here. So plug in a third everywhere else. We'll get a equals, the numerator is going to be 1 plus 2/3, 5/3, over 4 times, and that last thing that's going to be a 1 plus a 12th there, right? 13/12. Okay, I think that's correct. Yep. And, we can multiply that out. I'm just going to leave it. It's not going to do much to multiply it out. And then b would be similar. We would cover up this one. We'd say z inverse should be -4 to make that 0. So then we go up here. We plug in a -4. We get 9 up there. Oh, no, we don't get 9. We get a -7, right? Because it's a -8 plus 1, -7. And then lastly, plug in a -4 here. We get 13. Okay, so those are our constants. And finally, we just use the table to do the inverse of these things. Therefore, h of n equals a times, and the table says this should be 3 to the n u of n. Just make sure that that's right. Where did my table go? Yes, I believe that is. And then plus b, and this would be negative a fourth to the n u of n. So for these particular values of a and b. So there's the inverse. Okay. Any questions? Okay. So let's talk about other things we can do with this Laplace transform and Z transform directly. Usually these will be more important than actually taking an inverse. So a couple of nice things intuitive things you can get directly from the pole zero locations in a rational Laplace transform or Z transform. Okay, so one is you can interpret the frequency domain. So let's suppose that your system is, let's suppose that it's stable, and we want to know what is the, well, I mean, really what we're talking about is we want to evaluate the Fourier transform, because if it's stable, then the imaginary axis is in the region of convergence, so we could evaluate the Fourier transform directly from the Laplace transform. So suppose the system is stable. Interpret x of f from poles and zeros. Okay, so an example will help here. Let's say here's the S-plane. So this is the space of S for our Laplace transform. And we have a couple, let's say we have some poles. They all are going to be on the left half plane because the system is stable and causal. Say it's like this. And some zeros. Okay. Now, if I want to know now, what is the frequency response of this system? Well, remember that we said we can evaluate any rational function based on the distance to the poles and the zeros. Okay? So, in other words, suppose we want to know what is the magnitude of this Fourier transform around this point here. Well, the magnitude, we'd look at the distance to the zeros, and we'd multiply those, and we'd look at the distance to the poles, and we'd divide by the distance to the poles. So we already had a picture like this in a previous lecture. And that would tell us this magnitude. But very quickly we can see that when you're near a zero, this magnitude is going to be low. It'll be a little dip here because it's near a zero. You're multiplying by that small number. When you're close to a pole, here, your magnitude will have a local peak. Okay, I'm drawing a graph vertically here because the Fourier transform lives on this axis. So let's imagine that I've turned the graph to the side, and this is high magnitude, and this is low magnitude. Okay, so I'd have a little peak here. Actually, maybe there's a better way to draw this. I can just say high magnitude here. And that's because I'm sort of close to a pole. If I was very close to a pole, it's going to be a very strong peak in the magnitude. And this is a low magnitude. What's going to happen as I get to very high frequencies? Is the magnitude going to be falling off or staying the same or what? Well, I've got 3 poles here, and I've got 2 zeros. So as I increase all of them, the poles are going to win out. There are 3 poles, so it's going to be dividing by bigger and bigger numbers. Okay, so it falls as the frequency increases. Okay, so the point is I can easily understand like the frequency response, at least I can get a rough picture of the frequency response just by seeing which zeros and which poles are close to this imaginary axis. All right, let me do it in the Z transform and see if this starts to sink in. Suppose that you have, here's the Z domain, and here's the unit circle. And suppose you have these poles and zeros. You've got a 0 here, you've got a pole here, and a pole here. Okay, and it's the causal system. Is this stable? It's stable. All the poles are in the unit circle. Okay, now where might, okay, so the frequency response, the Fourier transform lives on this unit circle. Of course, we know that frequencies, up here I didn't label the frequencies. We knew this was f equals 0, but I didn't label how far down it was for different frequencies. We didn't have labeling. But for this one, we always know this is f equals 0, this is f equals a half, here's f equals a quarter, f equals negative a quarter. Okay. Now, where is going to be the highest magnitude of the Fourier transform? Around what frequency? What was that? Yeah, something up here around this pole. And so you just have to, let's say we're approximating here. So we have to say, well, how much is that? You said maybe a third. Looks about correct. So in other words, the Fourier transform, we know that this Z transform has an inverse that has an impulse response that's stable. We could take a Fourier transform, and we know it would get us, and of course for discrete time, you only ever care about frequencies up to a half and negative a half, right? So here are the frequencies. And basically what we're saying is the magnitude of x of f is going to have a peak somewhere around a third. It's going to be like something like that, because it has a pole right next to the unit circle. So it should be pretty sharp peak, both of these. Okay, and maybe its lowest point is going to be over here at the low frequency. So it might be something like that because there's a 0. One thing to notice here is someone asked in previous lectures, do the zeros matter? Okay, because the poles are determining stability. The poles are determining a lot of things. What do the zeros matter? Well, here we directly see the zeros actually do affect the magnitude of the frequency response. They can cause a local null in the frequency response. Okay, so this is one of the few cases where the poles are going to play a big part of this frequency response. Now, the other thing you can do very quickly from a pole zero plot is you can learn also, the second thing here is time domain. The time domain response of this system. Well, we just went through the exercise of doing an inverse Laplace transform. The inverse Laplace transform meant we did a partial fraction expansion and we invert each pole. But the main idea there is that each pole is going to become a term of your time domain impulse response. Okay, so the impulse response is simply going to be, the zeros again don't really matter here. It's going to be a sum of terms, each one corresponding to a pole. Okay, and in fact, the poles are going to be turning into exponentials in the time domain. And the real part of the pole determines the exponential decay, if you look at that table, right? So the more negative the real part is, the further it is away from the imaginary axis, the quicker that term decays exponentially. Sometimes you want to know, not only is your system stable, but how quickly does it return to 0? 0 represents like an equilibrium position. How quickly does it return? Well, that's going to say, if the poles are further from the imaginary axis, then it is going to respond very quickly. If they're very close to the imaginary axis, meaning you're sort of almost unstable, then it'll stay a while before it dies off. Of course, and what does this imaginary part mean? That's the oscillation that's associated with that term. Okay, so if you So there's a certain frequency, and it says, well, this particular term of the time domain oscillates at that frequency. So you learn a lot just by looking at the location of these poles and zeros. We can get the frequency response, the time response, at least roughly, very quickly. Let me demonstrate that for filter design, this frequency response technique is actually used in practice. And here's an example. So we talked about filters a while ago, and that we know what the ideal low-pass filter is, but designing practical low-pass filters requires some creativity with a limited number of components. And so there are various well-known filter designs, and one of them is this Butterworth filter. Okay, so here's the Wikipedia page for the Butterworth filter. It's a low-pass filter, but using a limited number of, limited degree of a Laplace transform, basically, to do it. Now, what I want to point out is this. So the Butterworth filter, they show you can implement it with some circuit components. And you can get a higher order Butterworth filter by putting more components in here. Okay? And it's a specific design to give you a nice, here they're showing the gain of the filter. As it falls off, it's meant to be a low-pass filter. And the red is showing the group delay of this filter. Okay, that comes from the phase. But what I want to point out is this picture right here. This is actually the Laplace transform. Okay? And these are the poles of the Laplace transform. The Butterworth filter is designed, you can think of it as being designed in the Laplace domain. Now, in order to be stable, you have to put all the poles in the left half plane here. And it's designed to have 3 poles and no zeros, so that when you're in these low frequencies, you're near the pole. Okay? But when you get away from here, you're far away from the poles, and that's why the frequency response drops off. So you can kind of see how you might use the Laplace transform or the Z transform to design your filter response. If you know you only are allowed a certain number of poles or a certain number of zeros, because those correspond to how many components you would have to use, then you could place them strategically to give you the frequency response you want. And that's a part of filter design. Okay? So this is a continuous time filter designed that way. Now, you could imagine there are other techniques that give you other low-pass filters. And just to show, like the Butterworth filter happens to place the poles on a circle. Okay, so that's interesting. Higher order one would place more poles in this circle. Now, you can also, here's some other well-known filter designs. There's the Butterworth filter, and you have these other ones, Chebyshev, elliptical, and they all have different designs. But just as an example, notice that you can get a really sharp transition, but you get these waviness in the passband and so forth, so there are trade-offs. But let's go look at the elliptical filter to see where they place the poles and the zeros. And here, the poles, now this picture doesn't exactly correspond to the Laplace transform. They've sort of mirrored it on both sides of the axis. The Laplace transform, of course, we can't have poles on the right side here. It would be unstable. But for various reasons, this picture is helpful sometimes when they mirror it. Okay, so, but just the actual placement of the poles are on this ellipse. But the other thing that helps this elliptical filter is you can see here they've placed some zeros right on the imaginary axis. So you use the placement of the poles and the zeros together to give you a very sharp transition from being near the poles. The magnitude here should be very high. And once you get up here, you're near zeros, and you drop very quickly towards 0. Okay, so that's why you get this sort of behavior, where you drop off quickly and you actually hit some zeros. Okay, so great. Now we're ready to do our demo, because that's all we have time for. Okay, boy, always want to fit too much in, but I think, okay, so how do you use all this for control? Well, first of all, what if you have a system that's unstable? Let's say H is our system. This is LTI. And this is unstable. So think, in real life, many examples of unstable systems. For example, flight of a rocket, like a space shuttle, okay, launching. Or even like military aircraft. These things are unstable in the sense that they're the actuators that are propelling them if the alignment gets a little bit off of a rocket, it wants to get even more off. It doesn't want to return back to its equilibrium position. All right. So if you were manually just controlling the position of these thrusters, you'd have a very hard time flying this thing because it's going very quickly and it's going to want to start spinning. All right. So what you can do is you can put in electronics that help you control it, that are going to they're going to do something automatic to help you control it. Now, one way, this is here's one idea. What if you design a system G such that you're going to put the inputs to your unstable system are going to be controlled by this automatic system G. What can this do? Well, it's possible. Okay, it's possible for zeros of G to cancel poles of H. Why is that? Because the combined system now is going to be G of S, H of S. Is now, our convolution rule says that from input to output now, the transfer function is going to be G of S, H of S. And whenever you have this product, you get poles and zeros cancel if they're the same. Okay. Okay. And when a zero cancels a pole, the region of convergence expands out to the next pole. All right. Now, this is so-called open loop control. And this is not robust. Can someone say why this would not be a robust way to control a system? To cancel a pole? Yes, exactly. You need the zero to exactly cancel the pole. Any mistake, tolerance in your components or whatever, you're not going to be stable. So you're essentially trying to, it's like you're trying to control this rocket blindfolded. You're anticipating everything it's going to do and try to control it that way. Now, closed loop control is the more interesting way. Feedback control. And here what you're going to do is something of this form. You have your unstable system H. You have your, and you actually design a controller. Here's your controller that's in a feedback loop. So let's say you have some input x of t that's coming from like a pilot or something that's trying to control this thing, and you have g feeding back to try to make this stable. So out comes y of t. So even if h is unstable here, what we can do is we can analyze what is the total transfer function of this system, and we'd analyze it by doing the following. We'd say, well, this is x of s, this is y of s, this is g of s, y of s. This is then the sum, right? X of s plus g of s, y of s. And this here is going to be, just multiply both by h, g of s, h of s, y of s, and that equals y of s. So we get our equation here. We put like terms together, and we get that the transfer function is this. And the main point here is that now we would look at the poles of this system, and the poles of this final system are not just determined by the poles of h of s. In fact, the poles of h of s cancel, and really, so they no longer determine stability alone, and instead you care about you look at this whole quantity here. And this is much more robust control. Okay. So what do we have here? So by the way, these types of equations, I mean, you know enough now that you could derive something like this. It turns out that a formula like this, these have names and they're known in control literature and they're studied very well to figure out how do you design G so that this quantity is stable, all right, and has a good transfer function. And so what we have here is an inverted pendulum demo. All right. So what's the inverted pendulum? So the inverted pendulum is an unstable system that's just the following. You have a motor that controls side-to-side movement, and you have another axis here that has no motor on it. Okay, just falls, right? And what we want is to hold it up like this. Okay, it's difficult to do by hand, but you've done this with like longer sticks, like broomsticks at home, you know, and you can balance it. But the way you're able to balance is you're using feedback, right? You're understanding, oh, it's tilted, I'm going to move. So we have two sensors in this system that'll give us feedback. You see these wires here. This is not a motor, but it is a sensor. We know the vertical angle of the stick, and we know one more thing. We know this position, which we're only going to use towards the if we want to like center it. Okay, but really this angle is going to be the main thing we use to make it stable. So we know the angle, and we have a motor that can turn this. The point is, can we automatically get it to stay up? It's like a Segway, right? So first of all, it's pretty clear that this system is unstable. Oh, I lost my pen again. There it is. Okay, let me just write down a formula here so we can see how it's unstable. I mean, we know it's unstable, but this is the system we want. We have the pendulum, and we're able to apply a torque here. And out of this, we have two sensors. We have position, and we have the angle. And we're just going to use the angle first here. Okay, so what we're going to do is we can feed both of these back, although we won't use the position right now. And we get a controller. And we just want that to go supply our torque for now, just to make it stand up. Okay, in the end, we'll also have like an input signal that might tell us where we want this pendulum to move, and it should move there. Okay, now, the question is, how do we model this pendulum? Okay, so it turns out that there's a problem in the book, which you can see, that'll ask you to derive the dynamics of this pendulum. Okay, and then actually you calculate it from a simpler model of a pendulum. In the book it says you have some acceleration, you have a pendulum that's not spinning but is on some wheels, and it's got, again, some angle theta of t, and it has, in the book, the one has some mass here, and everything else is negligible. And you work out some equations. You say, okay, well, the mass causes a force that way, that causes a torque that way. You can calculate out some equations. For example, you get something like this. Gravity times sine of theta minus the acceleration cosine of theta equals the angular acceleration here, okay, times some constant L. Okay, so you get some equation like that. Now, notice this is a nonlinear differential equation. Okay, our signal theta here is in a sine and a cosine. So what we've learned is how to control linear time invariant systems. Here we have a time invariant system, but it's nonlinear, and that's frequently the case. And when that is the case, you often do linearization. So that means for small theta, we can just substitute in theta Sine of theta is approximately theta. Cosine of theta is approximately 1. Put those in and simplify, and now you get a linear differential equation. G theta of t minus a of t equals L d dt squared theta of t. Do our Laplace transforms. G theta of s minus a of s equals L s squared theta of s. Therefore, put it all together, theta of s over a of s, a being the input. This is exactly 1 over g minus Ls squared. And we can separate those into poles by saying that equals negative 1 over L s plus square root of g over L s minus square root of g over L. So poles, we have 2 poles, no zeros, and the poles are at plus minus square root of g over L. Okay, is this stable? It's causal. Is it stable? We have a pole here and a pole here at g over L. So it's not stable, right, because it has a positive pole. Now, what we're going to do is 2 things. We're first going to apply feedback. Sorry, I may run a couple minutes over. So what we're first going to do, so what we can do now is we can model, so we can say our pendulum actually here, we now have a formula for it. Okay? It's a c over s plus alpha, s minus alpha, where of course alpha was this square root of g over L business. Okay? But anyway, it's a 2-pole system, and we want to control it to be stable. So the first thing we might do, the first feedback system you might think of trying would be very simple. It would be the following. You do, let's just do a proportional feedback. Like this. So here's theta s. What we're going to do is just multiply by some constant, negative, I'll call it K2 because that's what the software calls it. Okay, so in other words, if it starts to fall, the system is going to try to catch it, right? It's going to move, apply torque in the direction it's falling. All right, let's see if this set up for that. Yes. Okay, so I have some gain that's going to try to catch this system if it's falling. Anyone think they know what's going to happen here? All right, so once I stand it up, it turns on. Okay, it's pretty good at catching it. It shuts off when it gets the angle too big. Let's run it again and see if we can identify. It's sort of working. It's sort of working, right? It's holding it up. I have to keep it from the angle going too big. But it's oscillating a lot. Okay. Now, if we work out where the location of the poles and the zeros are, well, it's oscillating. We have this type of feedback. We'll see, and you can work this out because we don't have time here. The 2 poles, one was positive, one was negative, as you apply proportional feedback, the poles move together towards the imaginary axis. If you keep applying enough feedback, which we have, they move up the imaginary axis. So it's actually not stable. They're right on the imaginary axis, so they're not stable, but they're almost stable. So that's why it sort of stands up. But what would you expect to happen to a system that has poles on the imaginary axis? You would expect for, so if it has poles on the imaginary axis, you would expect it to just be an oscillator. It would be like a sine wave. And maybe it would start oscillating bigger and bigger, which is kind of what this is doing. Now, to fix that, what we do is we apply a second feedback here, which is simply that we simply do this. We also do a derivative control. So we take a derivative here of theta, and we add that in. Okay. Now, if you work out the algebra for what this allowed you to do, this becomes negative k4 in our software. This gives you another degree of freedom. Rather than just one parameter, that parameter allowed us, when you work out the math, to move the poles in and up the axis. This parameter is going to allow us to shift both poles to the left if it's chosen correctly. Okay, so it's actually going to be very stable. So what I'll do is just plug in the other. I'll put in that feedback as well. All right, and so it's actually very common to use this control that uses proportional feedback and derivative feedback. And if you want a third degree, a third parameter, you put in integral feedback. And this is known as a PID controller, proportional integral derivative. Very, very common, simple controller that's used to control a lot of things. So we're just using the proportional and the derivative part. And so now when I put it up, hopefully it works very well. And so look, it's so stable, you can't even, it looks like it's solidly glued onto the piece. I'm just keeping my hands here because it'll just drift and then shut off. Someone want to come touch it and see, come up and see how it, I'll just keep it, I'll keep my hand here to keep it. It feels solid, right? It's pretty amazing that it's just that there's no actual motor here. So the other thing we can do, but we're out of time, is I'll go ahead and shut it off. So the other thing we can do is we can additionally use the position sensor to keep it in the middle, or we can get it to track a position. I'll just turn that on as we end the class so you can see what that looks like when it stabilizes itself in the middle. And again, the way we do this is we just we do another control loop using position, and we use proportional and derivative in that control loop as well. So this time, it should try to stay towards the middle. And if you knock it away, it comes back. All right. Feel free to come play with it. Yeah. What you're right. They do interact with each other. The way that if I had more time, the way I derive this outer loop is you first just assume the inner one is like perfectly stable, and just go control the outer one. But in fact, to correctly do it, you would take the transfer function that we derive. We have a transfer function for the balancing, and it does have poles. We've just moved them way over into the left half side. Those poles, when you then look at the outer loop that you're trying to stabilize, you have to take those poles into account. And if you, for example, if you try to center too aggressively, you might cause those poles to be unstable again. So if you take them into account, then you can make sure the whole thing's stable. Okay, that's awesome. It's interesting that we just linearized. So like when it gets too far off, the math isn't quite correct anymore. But as long as it stays in its equilibrium, and that's how a lot of control is done. If they, like a lot of control for like flying a rocket or a space shuttle, they linear, or like even just like a military, fighter, they linearize around where they want it to be, and they just have to make sure they stay in that region for the control to work.
Thank you.
Thank you.